Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 7.4, the rational zero theorem and the fundamental theorem of algebra. Video 5, the fundamental theorem of algebra, complex zeros. In this video, there's not going to be a whole lot of examples. It's more of explaining the concept. And then in the next video or two, we'll illustrate that concept. But let's start with the fundamental theorem of algebra. Now, the fundamental theorem of algebra actually has about 3 versions. They all say the same thing, essentially. It's hard to tell that at times, but here's the 3 versions that you could run across. Version number 1, if f of x is a polynomial function, then f of x has at least one zero, which may be real or complex. So in other words, as long as we have a polynomial function, there has to be at least one number that makes it equal to 0. And it may be complex, meaning that it has i's in it. Version number 2. If f of x is a polynomial of degree n, so the highest power is x to the n, then f of x has at most n unique zeros. In other words, there's a limit to how many solutions this equation can have. Oops, come back, please. Not sure what happened there. There's a limit to how many solutions this equation can have. F of x equals 0 has at most n solutions. And notice I said at most n unique zeros or n unique solutions. So if something shows it more than once, we don't count it more than once, but it can't have more than the highest power. And this kind of makes sense because if we had a function that started with x to the n and then some stuff afterwards, and then we tried to factor it completely, well, I've only got this many x's to distribute across my parentheses. So there's n factors at most, and each factor produces a 0. So you can kind of see that there can't be more solutions than whatever the highest power is. Okay. And then version 3 says, if f of x is a polynomial of degree n, then f of x has exactly n zeros counting repeats, in other words, multiplicities. So there's 3 different variations that all essentially lead to the same result. The actual fundamental theorem of algebra is the first statement, but a consequence of it is the second 2. The one that we're going to be using is the third one, that if f of x is a polynomial of degree n, then f of x has exactly n zeros counting repeats, i.e. multiplicities. In other words, if we took all the multiplicities and add them, it should match the highest power. All right, so for example, this is a real quick example. Consider the function f of x equals the square of x minus 1 times x squared plus 4. Now, we could multiply all this out and make it look like a polynomial function. But if we're going to put it equal to 0 and solve it, then we want it factored, and that's precisely where it is right now. If we were to solve this, we would get x minus 1 equals 0, and we would get x squared plus 4 is equal to 0. If we solve x minus 1 equals 0, that's easy. We get x equals 1, but keep in mind that this has a multiplicity of 2. The multiplicity is the power that was on the factor. But if we solve x squared plus 4 equals 0 by subtracting 4 from both sides, to get x squared equals negative 4, square root both sides, which would invoke a plus minus. And then we get x equals plus or minus 2i, because the square root of negative 4 is 2i. Then our solutions, or our zeros, are x equals 1, x equals 2i, and x equals negative 2i. And keep in mind that the first 0 has a multiplicity of 2. All 3 versions of the fundamental theorem of algebra were satisfied. Version 1, there's at least one 0. Yeah, we found 3 of them. Version number 2, there's at most n unique zeros. Well, in this function, this is a 4th degree polynomial. It's not immediately evident, but if you remember the discussion we had about calculating the leading term so that we could discuss n behavior, you could figure out that the degree of this polynomial is 4. and we had 3 zeros. So there were at most 4 or less, which is what we had. And the third version of it says there's exactly n zeros counting repeats. In other words, counting multiplicity. What that means is, since the x minus 1 was actually squared, we could have thought about it as x minus 1 written twice, put each one equal to 0, and solve, and we would get the same solution twice. This is the same as saying x equals 1 with the multiplicity of 2. Shows up 2 times. So if we count x equals 1 twice, we get 1, 2, 3, 4 solutions. So regardless of which version of the fundamental theorem of algebra you look at, they all essentially lead to the same thing. It's not clear that the first version leads to the second two. That's a proof for upper classes that we're not going to worry about. Let's get rid of these underlines here. Oops. All right. And let's also get rid of the all that stuff. Just trying to make this clean so that when we can save this as a PDF, it's not all littered. I know sometimes that happens. All right, so we'll leave it there, right there. All right, so what's the thing about complex zeros? Because that was the other part of the title. Complex zeros. And when I say complex, I really mean not real. Let's get rid of that underline there. Complex zeros. If f of x is a polynomial with real coefficients, let that sink in for a second. Polynomial function. Let me spell polynomial correct. I know you see all this stuff that's hidden, big deal. If f of x is a polynomial with real coefficients, so the numbers in front of the x's don't have i's, then complex non-real zeros occur in conjugate pairs. Now, what does that mean? Well, it means this. Specifically, if a plus bi is a 0 of f of x, then a minus bi must also be a 0 of f of x and vice versa. The reason this is actually stems from the quadratic formula, loosely speaking, because when we got solutions that look like this, it's usually because we broke out the quadratic formula, negative b plus or minus the square root of some stuff over 2a. And sometimes this had a negative under it, which created an I with a plus minus in front. That's all this is saying, is that if you have something with an I with a plus in front, then the same solution with a minus in front must be a 0 as well. For example, and let me clean up this mess. For example, suppose f of x is a polynomial function with real coefficients, and when we put 3 minus 4i into the function, it comes out 0. Well, what else has to make it equal to 0? 3 plus 4i. So all that's saying is that, to put it loosely, ugly answers occur in pairs. To be honest with you, it's not just complex solutions, non-real solutions like this. In an earlier video, we saw something where this was a solution. So a lot of times ugly solutions occur in pairs because of the plus minus from the quadratic formula, and the ugliness of the solutions renders them, they look unfinished, they look similar, except one's a plus in the middle, one's a minus in the middle, and that's what a conjugate pair is.